We experience life as if time were a rigid, universal metronome, a steady rhythm where 1 second for you is identical to 1 second for everyone else. To see why that assumption fails, imagine you have a twin. You stay on Earth while your sibling lives on the International Space Station for 6 months. When your twin finishes their mission and returns to Earth, they are technically younger than you are. This age gap is a direct result of the physics of motion and mass. In orbit, the astronauts' environment caused their seconds to physically stretch, meaning they accumulated less time than someone on the ground. Time functions as a fluid dimension caught in a continuous physical tug-of-war between two massive forces. To understand the aging gap, we have to measure both of them. The first force pulling on time is velocity. Albert Einstein's theory of special relativity established that the speed of light is the absolute cosmic speed limit. Because that limit cannot be exceeded, the progression of time itself must change when objects move at extreme speeds. Consider a light clock measuring time by bouncing a single light beam vertically between two parallel mirrors. As this clock moves forward at high speed, the beam can no longer travel in a short vertical line. It must instead trace a significantly longer zigzag path. Since the speed of light is constant and cannot speed up to cover that extra distance, the light beam takes longer to complete its journey between the mirrors. Consequently, each tick takes more time to occur. This establishes a definitive rule. The faster an object travels through space, the slower it must progress through time. The second force is gravity. General relativity suggests we move past the idea of gravity as an invisible pulling force, and instead view it as a physical feature of the universe. Massive objects like planets and stars warp the very fabric of space and time, a unified medium called space-time. Think of a heavy ball stretching a trampoline. Stretching this fabric doesn't just change the geometry of space, it pulls on the duration of time. In these deep gravitational dips, the intervals between seconds are physically elongated, causing the clock to tick more slowly. On Earth, the closer you are to the planet's massive core, the more space-time is stretched. This means time moves slightly slower at sea level than it does at the top of a mountain. Gravity essentially anchors time. The stronger the gravitational pull, the slower the progression of the clock. Your astronaut twin is currently living directly inside these two effects aboard the International Space Station. Orbiting 400 kilometers up, weaker gravity speeds the astronaut's time up by 5 microseconds per day. However, traveling 28,000 kilometers per hour slows it down by 28 microseconds. Velocity wins the tug-of-war. Their time passes 23 microseconds slower per day than yours. By combining these two equations, we can mathematically prove why the twin in orbit returns home younger than the twin who stayed behind. These mechanics become even more extreme when we move 20,000 kilometers away from Earth to the orbit of GPS satellites. In this high orbit, the tug-of-war flips. The satellites move slower than the ISS, losing only 7 microseconds to velocity, but their extreme distance from Earth's gravity speeds their clocks up by 45 microseconds. At this altitude, gravity is the dominant force. Satellite clocks run 38 microseconds faster every single day than the clocks on our phones. This proves that time is entirely subjective. Altering your position or speed in space completely changes the rate at which you age. While 38 microseconds seems negligible, it represents a massive hurdle for modern engineering. If engineers didn't program satellite clocks to tick slightly slower to compensate for Einstein's math, the timing errors would compound. Within a single day, your GPS navigation would drift off course by 10 kilometers. Whether we are navigating across a city or orbiting the planet, our technology and our bodies are governed by the fluid connection between space, speed, and gravity. Because velocity and gravity dictate the rhythm of our clocks, every astronaut returning from orbit has technically stepped into our future. They aren't just exploring space, they are navigating the physical mechanics of time.